For this topic, we're talking about related rates in calculus, and now we're to the point where we have usefulness. It is some application to what calculus is about and how it's used in the real world. Okay, so as this says, we deal with rates of change in calculus. We've talked about that. Rates of change is the derivative. A rate of change is like the slope on a curve. We describe this change with words like increasing, decreasing, growing, shrinking. This change happens over time, so we're literally talking about the derivative of a quantity with respect to time. So here's an example. George grows at a rate of 3 inches per year. So if I wanted to show that, we're thinking about what we're looking at here. The thing that's changing is George's height. It doesn't say that specifically, but we're hoping this is his height and not his waistline. Otherwise, that's going to be bad for him real soon. But if we're talking about height in this case, so let's think about what's changing. We're going to show this as a derivative. So what's happening here is we're looking at the change in his height as it relates to time. When we're talking about rates of change, it's always with respect to time. And so I would show this quantity here, 3 inches per year. It's his change in height with respect to time. And so it's just going to be 3. And we got to make sure and put the proper label on here. Since it's 3 inches per year, well, our height is on, if you notice here, our height is on top. So it's changing 3 inches in height. Time in this case is per year. And so the label we associate with this, his change in height, is going to be 3 inches per year. Okay, looks like that. If I want to look at something like this, my mutual fund is shrinking at a rate of 4 cents per day. Well, let's think about what's changing. We're talking about a change in, well, there's lots of ways I could describe this. Change in money, change in value. Probably going to call this a change in value with respect to time. And since this is shrinking now, we're looking at shrinking, this is going to be a negative 4, because it's decreasing, cents per day. And so we might say this, I don't know, cents per day. Or we could call this, I'm going to move this over. Oops. We could call it a negative 0.04 dollars per day. All depending on how we want to label that. Okay. Let's think about this one. The radius of a circle is decreasing at a rate of 4 feet per hour. There again, take a look. What's changing? The value that's changing is the radius with respect to time. Since it's decreasing again, we're going to call that a negative 4 in this case, negative 4 feet per hour. These are all rates, unit rates if you will. We talked about rates before. If I want to describe this one, the volume of a cone is increasing at a rate of 2 cubic inches per second. So we're looking at a change in volume. Volume is usually used with a capital T, or capital V, with respect to time. In this case, it's increasing, so we're going to have a positive 2, and they already give us the units here, cubic inches per second. Okay, so some guidelines for related rates types of problems. Here is just kind of a set of guidelines, good to follow. You do this in every single one of these types of problems. you should be pretty okay. Step 1. Make a sketch. Whatever you're given, make some sort of sketch. Draw a picture. Label all the dimensions that we know, or that are given, as variables, even if we know what the actual values are. Even if we're given a radius of 5, or a height of 7, something like that. In our original sketch, label it as variables, because some of those are going to be changing. Step 2, identify which variables are constant, which ones are changing. And you don't have to explicitly write this out, but sometimes it's helpful. Write down all that we have, all that we know. Again, if you're given some sort of rate, if something's changing, increasing, decreasing, growing, shrinking, okay, any sort of rate we want to write as a derivative with respect to time. Any kind of rate at all, any kind of change. Okay, step 3. Again, as you go through this, pause the video if you need to so you can get all this down, because these are important steps. Number 3, find an equation that ties all these variables together. If the problem's talking about area, we'll use some area equation. If it's talking about volume, we'll use a volume equation. This is where a lot of our geometry comes back into play. If you don't remember all those formulas, you can look them up. There's also a table in the back of your book, very back inside cover of your book, that'll has a whole table of formulas there for geometry. Okay, if we're dealing with right triangles, we can use Pythagorean theorem. If we're not using right triangles, if we're using other kind of triangles that aren't right, we could use some sort of trig equation, law of sines, law of cosines. Those apply to all triangles. Apologize for all the noise on the video. Hopefully this comes through and it'll be fine. So our next step, go ahead and differentiate. Take the derivative of our equation. Again, we're going to take the derivative with respect to time. Now, since it's going to be with respect to time, the variables are going to be different. They're not going to match up. So we're looking at implicit differentiation here. So you got to make sure and use your chain rule. Show the right notation. If you're taking the derivative of, say, a radius with respect to time, it's going to look like dr dt, where appropriate. If you're finding the derivative of the height, dh dt. Derivative of the area, dA dt, and so on. Always with respect to time. Then, just plug in all your variables that we know. Everything that we're given, plug in what we know, and hopefully you'll be left with just one variable to solve for. If there's not just one variable left, you might need a secondary equation. And hopefully there's somewhere in the problem it'll give you some clues to that as to how these different values are related in another way. And then last, go ahead, label your answer with the correct units, and be sure that you answer the question that's asked. If it's asked, whatever it's asking for, make sure that that's what you found, and give the proper units. Okay, so here's an example. Let's say we have a rectangle that's 10 inches by 6 inches, and the sides are changing. In this case, they tell us the length and width are both changing at a rate of 2 inches per second. Okay, so first step, how might this look? Let's draw ourselves a sketch. So we're looking at a rectangle. And we've got a length, and we've got a width. And so far, we know, again, we want to set up this rectangle with variables. And right now we know that the length is equal to 10, and the width is equal to 6. They give us a rate. They tell us the rate. Both the length and the width are changing at a rate of 2 inches per second. So, our change in length is going to be 2 inches per second. Our change in length with respect to time, of course. So dl dt is going to be 2. And our dw dt, our change in width with respect to time, is also 2. Okay, now let's see what they're asking for. Oh, really? I don't want all that linked together. Okay, so they want us to find the change in area. Okay, so we got to come up with an equation. Well, what's our area equation of a rectangle? Area is equal to length times width on a rectangle. So, if I want to find the change in area, I want to know the change in area with respect to time. This is what I'm trying to find. So, I'm going to have to take the derivative of my equation with respect to time in order to get this. Okay, so let's do that. Derivative of area with respect to time is going to look like this, dA dt. And when I take the derivative of the right side, well, I've got length times width. Right over here, length times width. I've got to use product rule. So I'm going to take the first times the derivative of the second. The derivative of width with respect to time. Again, this is implicit differentiation because these variables don't match up. Second part of my product rule plus the second, which would be the width, times the derivative of the first, dl dt. This is our product rule. Okay, now let's fill in what we know. Well, again, that's why we listed all this stuff out over here on the right. We figured out what we knew and labeled it. Now we should be able just to plug in and find what we're looking for. So, the derivative of area with respect to time. Our length over here is 10. And the change in width, they tell us, is 2. Plus, our width is 6. And our change in length is also 2. If we multiply that out and add together, it looks like 20 plus 12. We're going to get an answer of 32. Now let's think about what this is going to look like. Let's get the right units on here. Our area, well, area is in square units. So our change in area is going to be 32 inches squared. In this case, per second, because they give us that as our change in time. Just like this. Okay. Part B. They want to know the change in perimeter as this rectangle is changing. And again, think about what this is saying. We're looking at for every second, this length keeps getting 2 inches longer, and the width keeps getting 2 inches longer each second. So as time passes, this rectangle is going to keep getting larger and larger. Okay, so the second part, if I want to find the change in perimeter, well, I'm going to need a perimeter formula. Perimeter of a rectangle. This is 2 times the length plus 2 times the width. And what we're looking for, I want to know the change in perimeter. This is what I'm trying to find, dp dt. Change in perimeter with respect to time. So I need to take the derivative of this formula with respect to time. The derivative of perimeter with respect to time is just going to be dp dt. We're doing implicit differentiation. These variables don't match up. Okay, so now over on the next part, derivative of 2L, well, is going to be, the derivative of 2L is going to be 2 times dl dt. Plus the derivative of 2w would be 2, but since these variables don't match, this is going to be dw dt. And again, once we've taken the derivative, now we can plug in what we know. This is going to be 2 times, well, our dl dt is 2. It's changing at 2 inches per second on the length. Plus 2 times dw dt is also going to be 2 inches per second. And so I've got 2 times 2, 4. 2 times 2, 4. 4 and 4 is 8. Perimeter, well, that's going to be in just inches per second in this case. Alright, let's do another example. Just like the last one. Same idea, same concept. We've got our same rectangle actually, where we've got our length and our width. Our length is equal to 10. Our width is equal to 6. In this case, the sides are changing. It's telling us the length is decreasing at a rate of 2 inches per second. So the length is getting shorter. dl dt is getting shorter, so that's going to be a -2 if it's decreasing. And the width is increasing at a rate of 0.5 or 1/2 inches per second. So our width is increasing, so that's a positive 0.5 per second. Again, let's find the change in area. Well, we just did that. We know that when I take the derivative of that, I get the change in area was the length times the change in width plus the width times the change in length. Same idea, same formula, same derivative. We just have different values to plug in for this one. So the length is going to be 10. The change in width is 1/2, 0.5. Our width is still 6. Our change in length is -2. So multiplying that out, we're going to get 10 times 1/2 is 5. 6 times -2 is -12. So this is actually decreasing by 7 square inches per second, because we're talking about area. Alright. You go ahead and find the perimeter on your own. We're going to move on to the next one. Here's another example. Let's look at a right triangle. It has legs of 30 feet and 40 feet, and those sides are changing. So we're looking at a right triangle here. And if the short leg is decreasing at a rate of 3 feet per second, and the long leg is increasing at a rate of 5 feet per second, we're going to find certain quantities here. Okay, so we've got a right triangle. Even though we know 2 of the sides, we're going to label these with certain variables. Now we can use whatever variables we want, but if you recall, a right triangle, we most often like to use A, B, and C as our hypotenuse. Remember, the legs are 2 sides that make up the right angle. Our longest leg, or longest side, is the hypotenuse. It's opposite the right angle. And it tells us the short leg, well, it doesn't really matter which one's the short here, other than let's just let A, if A is the 30-foot leg, then the short leg is decreasing at a rate of 3 feet per second. So the change in A with respect to time is going to be a -3. It's decreasing, it's getting shorter. And our other leg is 40, and it's increasing. So the change in B with respect to time, it's increasing. So it's going to be a positive rate of 5 feet per second. So we've got our figure, we drew our sketch, we've got all of our data labeled here. that we know. Now let's come up with an equation. Okay, so for part A, it wants to find the change in hypotenuse. So in this case, our hypotenuse is C, so we're looking for the change in C with respect to time. Okay, and these variables, so coming up in the equation, how do I find C? Well, we know that C squared is equal to A squared plus B squared. So I'm going to need to take the derivative of this equation with respect to time. So take the derivative with respect to time of all of this. Okay. So when I take the derivative of C squared, I'm going to get 2C, and then of course times dc dt using our chain rule, plus, equals, ahead of myself there, equals derivative of 2a, of a squared is going to be 2a times dA dt. Derivative of a squared with respect to time. Derivative of b squared with respect to time. 2b times dB dt. And so, if I plug in stuff, we'll get to that one in a minute. So I'm going to have 2 times, C. We need to find what C is. Hopefully, using your Pythagorean theorem, you can find this. We know a squared plus b squared equals c squared. If a is 30 and b is 40, we know this is going to be 50 with a 3, 4, 5 relationship. So we're going to have 2 times c, which is 50, times dc dt equals 2 times a. 2 times a is 30. I have no sorts of room here. We're going to come back to part B in a minute. I'm going to take up some of that space. So I'd have 2 times 50 dc dt equals 2 times a, which is 30, times dA dt, which we found over here was negative 3, plus 2 times b, b was 40, dB dt is 5. So now we just need to solve this for dc dt to find the change in hypotenuse. And we're going to get something like 100 over here, dc dt. This is going to be negative 180 plus 400 is that right? Yeah. Which is going to equal 220 dividing by 100 dc dt gives us 2.2. We're looking for that length, so that's going to be in feet per second. Okay, now I'm going to make more room to get our change in area for part B. Okay, so to find the change in area on this, area of this triangle, remember area is equal to 1/2 base times height on the area of a triangle. And we want to know the change in area with respect to time. So we're going to need to take the derivative of this equation with respect to time. Derivative of the left will have change in area with respect to time. And then we're going to have to use the product rule again. So 1/2 times base times height. Well, let's think of let's put this 1/2 with the base. This is our first. Height would be our second. So the first 1/2 base times the derivative of the second would be dH dt plus the second times the derivative of the first. Derivative of 1/2 b is going to be 1/2 times b, the change in b, so that's going to be dB dt. Now, we just got to figure out what's our base and what's our height here. Well, in this case, since we've got a and b, we just need to assign one. It really doesn't matter which. We end up with the same sort of equation here. If we want to let our a be the base, let's let a be the height. Let's let our b be the base, b for base, a for height. We can just plug in here then what we know. So we know we're going to have, this is going to be 1/2, the base, which is 40, times the change in height, dH dt is going to be -3, plus the height, which is 30, times 1/2 times dB dt, the change in the base was increasing at 5. So as the base increases at 5 and the height decreases at 3, we'll end up with a change in area of, well, this is going to be -60 plus, I believe, 75. Check my math on that. Looks to me about 15, and since it's area, we're looking at square feet per second. Here's a famous example. We've got a ladder leaning against a wall. The lower end of the ladder is pulled away at 2 feet per second, and it wants us to find how fast is the top of the ladder coming down the wall. So again, looking at a sketch, we've got our wall here. Oops. Here's our wall, and here's our ladder. And our wall is vertical, so if it's vertical to the ground, we end up with a right triangle again. So we're probably going to want to use our A, B, and C for a Pythagorean theorem. In this case, we know they tell us the ladder is 13 feet. So here C is going to be 13. And the lower end of the ladder is pulled away at a rate of 2 feet per second. Well, let's think about what that's telling us. The lower end of our ladder is right over here, right here. And so if I take the end of this ladder right in this area, and it gets pulled away from the wall, take a look at what's changing. The ladder's not changing, it stays 13 feet. What's changing is my distance of B here. My length of this bottom part of the triangle is changing. So my change in B with respect to time is where the 2 comes in. And that B is getting longer, so it's going to end up being a positive 2. Now, for this, what it's asking for now, as that gets pulled away, it wants to know how fast is the top of the ladder coming down the wall. So if the top of the ladder right here is coming down the wall, as I pull this ladder out away from the wall, A is decreasing. A is getting smaller. That length A is what's changing. So this is what we're looking for. We want to know dA dt, the length of that side of the triangle as the other side is getting longer. Okay, so again, how do these variables relate? A squared plus B squared equals C squared. Like on the last problem, when we took the derivative with respect to time, we ended up with 2a dA dt plus 2b dB dt equals 2c dC dt. Okay, so for part A in our problem, it wants to know how fast is the top of the ladder coming down. So our dA dt, the instant the ladder is 12 feet above the ground. Well, over here, when it's 12 feet above the ground, our A is equal to 12. We know that our C is equal to 13. We just got to find B. And so if I plug that back into my Pythagorean theorem, we know 12 squared plus B squared is going to equal 13 squared. That's another famous Pythagorean triple. So if you solve for that, you'll find B equals 5. Trust me on that. If not, go ahead, solve it yourself. Okay, and then we can just plug in what we know now, I believe, as long as everything's here. We know that 2 times A is 12. dA dt is what we're trying to solve for, so we're going to just leave that in there. Plus 2 times, we said our B equates to 5. Our dB dt, again, that's over here on the right, is equal to 2. This length along the bottom is changing by 2 feet per second. And that's equal to 2 times C. What's our C? Our C is 13. Times dC dt. Well, there's a good question. What's dC dt going to be? Again, think about what this stands for. dC dt is going to be the change in C with respect to time. Well, C is the ladder. The ladder's not going to change. The ladder has no change. It's 13 feet. It's not an extension ladder. Not as far as we know. As I pull the bottom here out away from the wall, the ladder stays the same length. So what's the change if C is a constant? If my ladder's a constant length, that change is going to be 0, because the derivative of a constant is 0. So now we should be able to solve for that. We'll have 0 over here. Over here we'll have 24 dA dt plus 20. And so solving now, dA dt, I'd subtract 20, divide by 24, subtracting 20, divide by 24 is going to give us a negative, what is that, 5/6. And again, this will be in feet per second. And this confirms that, yes, we said that as that ladder comes out, A is going to be decreasing, so we do end up with a negative value here. Second part of the problem, it wants to know the instant the ladder is 5 feet off the ground. So in that case, our A is going to be 5 feet off the ground, and it's going to be 12 feet away from the wall. And so we're going to end up with a lot of the similar values, just in different places in our formula here. 2 times A d80t plus 2 times 12 dB dt is 2 equals 2 times, again, 13, and this ladder's not changing, 0. And so solving here, we're going to get 48 over 10, or negative 4.8 feet per second. Okay, one more example, and I'll help you set this one up, but I want you to do it on your own, because this video is already getting quite lengthy. We've got a spherical hot air balloon. It's being inflated. And if air is blown into the balloon at a rate of 2 cubic feet per second. Okay, so if we're looking at, this is our change, this is our rate. In this case, the change is to the volume. We know it's volume because it's in cubic feet. With respect to time is 2. Two things they want us to find. They want us to find how fast is the radius of the balloon changing when the radius is 3 feet, and how fast is the surface area changing at that time. Put this back up here. Okay, that was 2. Okay, so we're going to need to find, if we know the volume is changing at 2 cubic feet per second, we're going to need our volume formula. Well, volume of a sphere. Again, if you've forgotten, look it up. It looks something like this, 4/3 pi r cubed. This first part, we want to know how fast is the radius changing. So we're looking for dr dt when the radius is 3. Second part, how fast is the surface area changing? Well, the surface area, we're just going to call that A for area, but surface area of a sphere is 4 pi r squared. So we want to find the change in area with respect to time. Try those. We'll talk about them in class. Let me see what you get. And then here's your assignment. On 153, 1 through 23 odd. And give some of those a shot. See you next week.